Math 230. This is Quest to College. I'm Joe Vasta, and we are going to be covering 1.2 and 1.3 pretty much in the same video. We usually will not do that, but in this case there is a good reason to do that. Now, before we get started with this, because this is kind of a weird thing, I'm going to give you the puzzle, and at the very end we'll answer this question. What do these letters have in common? So, what do those letters have in common? And that is the puzzle. Okay, 1.2 and 1.3. I drew part of downtown San Luis Obispo, and here is Chorro, Morro, Osos. Those are streets, and then we have Walnut, Peach, Mill, Palm. And at the corner of Palm and Osos is the library. When you go to the library, there's a parking structure right nearby, or you can park on the street, but they're meters. So when I first moved here, I found that I could park over here for free, somewhere here, and then walk to the library. So the deal with parking over here is then you have to walk, which is good, it's exercise. And you know, you might go like this. I'm going to walk to the library, and you go like this. And that. Now, when you walk from the car to the library, you have some choices that you can make. And so that's kind of what they're asking. How many direct routes are there from A to B, from your car to the library? And so, a direct route, or a route, maybe we'll say route, you know, goes directly. You're going to go here to the right, and then up, and then up, and to the right, and to the right. That's a direct route. Something that is not a direct route would be to the right, up, to the left, up, to the right, down, to the, because then you're just meandering. So a direct route, you're only going to go to the right, and you're going to go up. And so that's what we're doing. Now we could say north and east if we want, but I'll just use up and right. So, you know, let's say that we went up, up, right, right, right. So here's one of the ways. Up, up, right, right, right. You could go right, up, I'll put my finger here, and then right, right, up. And the list goes on. So maybe you can pause the video and see if you can figure out how many direct routes there are from A to B, and we know it's going to be probably more than two, because like 1, 2, and so you could either list them all or just kind of use your finger and count all the direct routes. Okay. So some of you paused the video and some of you didn't. This way, where you're just kind of listing them out and counting, is kind of not the best way of doing the problem. So we're going to break this problem down into smaller problems. And I'm going to ask kind of a really dumb question. But how many ways can you park your car there at point A and just stand there and go nowhere? Well, it's just going to be one way. Okay, so that's kind of a weird question. Now suppose the library was like right here. Suppose the library was right there. I'll put a bug with a we're looking at. How many ways can you walk from your car to this bug? Direct routes. Well, there's just one way. You just go that way. So I'm going to put a 1 there. And the bug left some sort of mark. It looks like the bug, what happened? Oh, it must have just, oh, because I put the red mark on there. Okay, it looks like the bug's bleeding. I didn't do, oh yeah, that looks kind of gross. Oh well, you can actually look at this when I PDF this. That will probably still be there. Okay, so suppose the library was there and you parked your car here. How many direct routes are there, or direct routes are there from your car to this bug? Well, it's just one direct way of getting there. And if the library was right here, there's just one way. Okay, so now, what if the library was there? and you parked right there. Well, there's only one direct route to go, and it would be by going up, and so I'm going to put a 1 there. Okay, so now here's where it gets interesting. If the library was right there, how many direct routes are there from your car to the library? Well, you can go to the right and up, so that's 1, and you can go up to the right, that is 2. So now we're going to go ahead and put the library there, and notice what we're doing is we're solving smaller problems, and then we're making them a little bigger until we get to the actual library. So watch this. If we put that there, let's just count them. We can go right, right, up. So that's 1, right, up, right. That's 2. Yes, I'm using my fingers. And then we can go up, right, right, which is 3. So this right here is 3. Now here's the whole magic of this. When I did those 3 routes, 2 of them came by going through this intersection. And 1 of them came by going through this intersection down here. And they added up and they got me 3. So look at this. 2 plus 1 is 3. Notice over here, 1 plus 1 is 2. So how do you think I'm going to get the number that goes here if the library was here? I'm going to go 3 plus this 1 right here. And that's going to give me 4. Because there's 3 ways I could have come from there, and 1 way that I can come from below. And that's the way where you go like this and up. Now some of you might go, why did you put the 4 over there and not over there? It doesn't matter, like where this 3 is, it doesn't matter if I put it there, 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 there. I didn't want to put it right on the intersection because then it would be hard to see in the video. So it doesn't matter as long as you put these red numbers close to the intersection. Okay, now let's go up and do the last road. Osos is the road. And so how many ways can you go from your car up to this intersection? 1 way. And it seems like where your car is parked, all those intersections where your car is parked get 1s on them. Okay, so now let's do what we did. You're always going to add the thing that's immediately to the left and the thing that's immediately below. You'll add those together. So look at this. 1 plus 2 is 3. 3 plus 3 is 6. 6 plus 4 is 10. So how many direct routes are there from your car to the library or from A to B? The answer is 10. Now when you're taking the test, you'll get a problem that's like this. You don't have to say 10 routes. You could just say 10. That's going to be acceptable. Okay, before we do the next one, let's go ahead and get into something you may have seen in another class. It's called Pascal's triangle. So Pascal's triangle. So this is a weird thing to be doing if you've never seen it before. It's going to be a big triangle with numbers in them, with the very top number being a 1. Okay, so that's our first row, 1, and then we have 1, 1. So you can see there's a triangle there, and on the outside of this triangle I'm always going to put 1s. And now this is the first time I have a number that's within the triangle. I am going to get this number by adding the 2 numbers above it. So 1 plus 1 is 2. Okay, so I have 3 rows. Here's the first row, the second row, and the third row. Now, the next row, I'm going to put a 1 here and a 1 there, because 1s go on the outside, and then this number right here sits below those 2 numbers, and you're going to get this number by adding them. 1 plus 2 is 3. 2 plus 1 is 3. So this row that we did is 1, 3, 3, 1. Let's go generate more rows. So the next row will have a 1 there. And then we have 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. And then we put a 1 on the outside. This is Pascal's triangle. Pascal studied this. I believe that this triangle was discovered long before Pascal. Let's continue. I have a 1 there. 1 plus 4 is 5. You're going to notice some things as you draw Pascal's triangle, is that there's symmetry. Okay, what do I mean by that? Let's finish this row and we'll talk about this. 4 plus 6 is 10. 6 plus 4 is 10. And 4 plus 1 is 5. And then we put a 1 there. The symmetry means is if you went ahead and divided this right in half like that, whatever you see on the left-hand side is mirrored through to the right-hand side. See the 3s and the 4s and the 10s and the 5s. And so that actually helps when you're doing rows, because if you've done everything right halfway through the row, then you're just going to copy what you did before. I'll show you what I mean. There's a 1 there. 1 plus 5 is 6. 5 plus 10 is 15. 10 plus 10 is 20. And now look, and now I'm writing down the hill. Look at this. 15. I mean, we can look up there and see that that's what it is. 6 and 1. So there's the symmetry. Let's go ahead and write another row, and then we'll talk about some other things. We have 1. 1 plus 6 is 7. 6 plus 15 is, what is it, 21. 15 plus 20 is 35. 20 plus 15, 35. Okay, so look, I plateaued there. Now I'm coming back down the hill. 15 plus 6 is 21, which we see over there. 7, 1. Okay, now, there's a few things we want to mention about Pascal's triangle. Is the row that we just did, even though it's the 8th row, 1, 2, 3, 4, 5, 6, 7, 8, this row is called row 7, which means the row above it is row 6. And this row right here is row 5. Row 4, row 3, row 2, row 1. This row right here, as uncomfortable as it may be, is row 0. The rationale behind that is, when you're looking at this row right here, you know exactly what row you're in because you look at the second entry, which is a 7. Okay, and so that's why they devised it that way. Computer science people like it because they like to start their loops. They like to start counting at 0. But in terms of like finding where you are, look, row 6 has a 6 as the second entry. There's other kind of neat things about Pascal's triangle, like you see the sequence 1, 2, 3, 4, 5, 6, 7. But here we see 1, 3, 6, 10, 15, 21. That sequence right there, and you don't have to write this down, that's a sequence of triangular numbers. So your first triangular number is 1. Your second triangular number is 3. I wonder why they're called triangular numbers. Your third triangular number is 6. It's because you can fit 6 little dots in the triangle. And then the next one is 10. I'll put it right here. 2, 3, 4, 5, 6, 7, 8, 9, 10. And if you play pool, you know, then the next one's going to be 15. So those are your triangular numbers. These guys right here, 1, 4, 10, 20, 35, those are tetrahedral numbers, which means I would have to like get marbles out. You could put 1 marble and then the next one forms a pyramid using 4 marbles. And then if you want another level to the pyramid, then it would take 10 marbles. So those are tetrahedral numbers. So there's lots of neat patterns that you see on Pascal's triangle. One other thing that I want to bring up is let's add up. Let's label these more. So this guy right here is row 4. And then this here is row 3. and then row 2, and row 1. So we'll put arrows here, okay? Row 3, row 4, row 5, row 6, and I'll just put an arrow there, though we don't need it. Let's add up row 3. So let's take a look at some sums. If we add up row 3, we get 1 plus 3 plus 3 plus 1, which happens to be 8. And we add up row 4, which would be 1 plus 4 plus 6 plus 4 plus 1, so that's 10, 14, 15, 16. So adding up row 4 is 16. The sum of row 5 happens to be 10, 20, 32. The sum of row 6 is going to be 20, 30, 40, 50, 62, 64. Look at this right here. Look at the sum of row 2 happens to be 4. The sum of row 1 is 2, and the sum of row 0 is 1. What kind of sequence is this? 1, 2, 4, 8, 16, 32, 64. This one's going to be 128. This is a geometric sequence. And in fact, you could look at it this way. 8 is 2 to the third, so the entries of row 3 add up to 2 to the third. The entries of row 4 add up to 2 to the fourth. The entries of row 7 add up to 2 raised to the 7th power. The entries of row 50, even though we didn't write it, add up to 2 to the 50th. Okay, so those are some neat things about Pascal's triangle. But now, let's make a connection between what we see in Pascal's triangle and what we see there, the numbers that I have labeled on the intersections. And so you might see what we have here. I'm going to circle it. This right here is downtown San Luis Obispo, where there's where you park the car, and there's the library. If you don't see it, let me go ahead and switch it around here. It's kind of at an angle. So there's Chorro Street and Morro and Osos, and you are taking walks to the library. Look, there's 1112, and look, it's the same numbers that you see in red there. What does this mean? This means that our direct route problems can be done using Pascal's triangle. So let's go back to this. Well, what row? So 10 was our answer. Let's highlight that or circle it in green here. And what row are we in? We are in row 5 to get that. So row 5 to get 10. How many different moves did we have to do when we went like this, this, up, and whatever? There's actually 5 of them there. See, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So here is the way to do this. You count, in each of these there's always 2 ups. There's 2 times where you have to go up. You count your ups, and there's 2 ups. And you count your number of rights. There are 3 rights. And you add them together. This is the quick way of doing these problems. 5 total. So this is the row you go to. Go to row 5. So we go to row 5 and we count over the number of ups, which is 2. 1, 2. Now, some of you might say, why didn't you start saying, counting right here, 1, 2? Because this right here is entry 0, just like that is row 0. So you put your finger there and you count over 2, the number of ups. Now, could you count over the number of rights, which were 3 rights? Yeah, so you would start here and you'd go 1, 2, 3. Because of the symmetry, you will get the same answer. Now, if some of you are like, whoa, what just happened? I think it's time to do a few more problems, and we can do these really quickly now. So let's go ahead and point out that 1.2 is Pascal's triangle. The homework for Pascal's triangle, I think, is create Pascal's triangle up to like row 9. So that's something you should know how to do on the test. And 1.3 is direct routes. Of the instructions that we wrote on the other piece of paper, it says how many direct routes are there from A to B. And so now this is what it looks like. Here's your car, here's the library. And so this is what I'm going to have you do. Count the number of times you would go up. 1, 2, 3, 4, 5. So there are 5 ups. How many times would you have to go right when you're traveling from A to B? Well, like, you know, if you went up like this, you would have to go to the right 2 times. So 2 rights. You would add that together and get 7 total. You guys are going to like this. Now watch. Here's Pascal's triangle. I'll try to fit everything in the range of the camera, and here's the problem. You go to which row? Go to row 7. So this is the row you're going to go to. Here's row 7. You put your finger on that first one, because that's entry 0, and you're going to count over the number of rights you have. 1, 2, 3, 4, 5. The answer to this problem is 21. So let's put that. So the answer, we'll just say 21. Now, you might say, hey, didn't you say you can count over the rights instead of the ups? Yeah, go to row 7 and count over 2. 1, 2. What do you get? 21. You're like, could I start by putting my finger over here and counting 5 the other way? Yeah, 1, 2, 3, 4, 5, you get 21. So there's lots of ways you can do this. 21 is the answer. Some of you might go, oh, I liked labeling the intersections. Is that a skill you need to know? Not for 1.3, but for 1.4, we're going to put blockades or barricades in there, and then we will have to go back to labeling the intersections. But for these ones, you'll get these ones done pretty quickly. There's 12 problems in your homework, and if you do it this way, you'll have your homework done in a few minutes for section 1.3. Let's go ahead and do one more problem, and then we'll answer the puzzle. Okay, so the next problem is problem number 3. We have Pascal's triangle. We'll put it back down when we need it. Okay, how many direct routes are there from A to B? Okay, so this is what we're going to do. We're going to count how many times we would have to go up. How many times would we have to go up? Well, 1, 2, 3, 4. So 1, 2, 3, 4, it's the same as counting the number of squares. So there are 4 ups. And how many how many times would you have to go to the right? 2 times. So 2 rights. And if you're still going, well, I don't get this ups and right thing, we'll take a little path from A to B. Let's see, you would go, let's see, one way you can do it is you can go right, and then up, up, up. Right, up, up, up. And then you can go right up. So look at this. That is a way you can go from the car to the library. And there are 4 ups and 2 rights, which makes a total of how many letters? 6. 6 total. So that would mean that's the row you go to. You would go to row 6. So putting down Pascal's triangle again. Go to row 6, which is right here, and count over 4, because you have ups. So don't count that first one, that's entry 0. So you go 1, 2, 3, 4, which is 15. Or you could have counted over 2, so we'd go 1, 2, which is 15. And that is the way you do these direct route problems from 1.3. Let's go ahead and finish up this video with a puzzle. What do these letters have in common? Okay, so maybe you thought about it and maybe you know the answer. Now, sometimes I'll ask a logic puzzle or something like this, and you may actually figure out something else using a different logic system than I used. But what these letters have in common, and they're just from the capital letters of the alphabet, they all have one hole in them. So these are all the letters that have a hole in them. So a letter that doesn't belong would be like S. It does not have a hole in it, you know, an enclosed region. And then B has 2 holes in it. So those ones don't belong. But these are all the capital letters where there's just one hole. Well, that finishes up 1.2 and 1.3. 1.4 is the next video.